A very useful tool in mathematics is the ability to approximate functions using polynomials. In this video, we will prove a fundamental theorem in this area that goes way back to my great-great-great-great-great-great-great-great-great-grandpa Brooke Taylor. Taylor's theorem gives us some measure of the accuracy of a polynomial approximation to whatever function you're interested in. But wait, I'm getting ahead of myself. Let's talk more about these polynomial approximations I've been referring to. To find a polynomial function p that approximates another function f, first choose a number c in the domain of f where the value of f and p are equal. C is basically like the center of the approximation. One way to think about it is visually the graph of p passes through the f at the center. Naturally, there are many polys whose graphs pass through that point, but we want to not only approximate the function at the center, but also near the center. One way to do this is to require that the rate of change or slope of the poly be the same as the slope of f at the center. Say we wanted to approximate the classic trigonometric function, sine near x equals 0. Using just these two requirements, we can find a basic linear approximation. Recall that the function that describes the slope of sine is cosine. The value and slope of the sine function at 0 are 0 and 1 respectively. Now, if we impose those two restrictions, we can conclude that the constant is 0 and the linear coefficient is 1, and will you look at that? A good linear approximation for sine around x equals 0 is the linear parent function y equals x. So this polynomial is pretty good near 0, but what if we want one that is a better approximation a little further out? To improve the approximation, we can also require that the second derivatives of the function and the polynomial are equal at the center. With these three requirements, we can now find a quadratic polynomial that can better approximate sine around 0. It's not too hard to find that the quadratic coefficient is also 0. This means that at 0, there is no quadratic that is a better approximation than y equals x. As you can hopefully imagine, we can continue this process indefinitely to find better and better approximations. So yeah, this technique is pretty cool, huh? Now, if we wanted to approximate the function somewhere other than 0, it is a lot more convenient to write the polynomial in this form. And if you differentiate over and over, you get this. Evaluating at x equals c results in these expressions. And because the value of f and its first n derivatives must be equal to the value of p and its first n derivatives at x equals c, we get all these coefficients. All right, so with these coefficients, we have the world-famous Taylor polynomial. Just so you know, some other guy named Colin tries to claim credit for this polynomial when c is 0. But yeah, that's just one specific case of the great Taylor poly. Okay, so now that you know what a Taylor polynomial is, let's be real. An approximation technique isn't very useful unless we have at least some idea of how accurate it is. To measure this accuracy, we can use the concept of a remainder, which is the difference between the exact value of the function and the approximate value. The absolute value of this remainder is the error of the approximation, and I'm going to call the remainder the Lagrange remainder out of respect for my favorite classic rock heroes, ZZ Top. So here we go, we finally made it, the Taylor theorem. The Taylor theorem is basically a recipe for estimating the remainder of a Taylor polynomial. If a function f is differentiable through order n plus 1 in an interval I containing c, then for each x in the interval I, there exists a z between x and c such that f of x equals the Taylor polynomial plus the Lagrange remainder. This is such a powerful theorem. Let's prove it. To find the remainder, assume x is an I and not equal to c. Define the remainder as the difference between the function and the nth Taylor polynomial approximation. Also, we will define g as a function of t, and the reason we're defining it that way is because differentiating with respect to t works out really nicely for all t between c and x. For a fixed x, g of c is 0 and g of x is also 0. Since g satisfies the conditions of Rolle's theorem, there must exist a number z between c and x such that the derivative of g at z is 0. Now we can evaluate g's derivative at that z and solve for the remainder. Since g of c equals 0, we can finally show that if a function f is differentiable through order n plus 1 in an interval I containing c, then for each x in the interval I, there exists a z between x and c such that f of x equals the Taylor polynomial plus the Lagrange remainder. QED, thanks for watching, and I can't wait to see you again.